Okay, so let's continue talking about seminorms as we were doing. So seminorms, fine. So in the last lecture we had introduced the notion of what a seminorm is, and with that we had also introduced the notion of what the Minkowski's functional is, and then we made an attempt to prove that the Minkowski's functional itself, it's a seminorm, if you recall, or rather we had, I guess we had just stated it where it clearly seemed to be a seminorm. So we will start with that theorem itself. Theorem: suppose A is a convex absorbing set. Okay, why do we require it to be absorbing? Because recall that the definition of by the definition of Minkowski's functional, for it to be finite we require the set to be absorbing. So suppose A is a convex absorbing set in a vector space X, then we have the following. Number 1 is that mu A of x plus y, this is less than equals to mu A of x plus mu A of y, right. Number 2, mu A times Tx is equals to T times mu A of x if T is greater than or equal to 0. Number 3, mu A is a seminorm, if A is balanced. Fine. Number 4, that if you choose this set B to be the collection of all elements X such that its value under the Minkowski's functional is less than 1, and if you choose C to be X such that mu A of x is less than or equal to 1, then B is contained in A is contained in C, and what we have is that mu B is same as mu A and it's same as mu C. Okay, so this was something which we had stated in the previous lecture, and let's prove it now. Okay, proof. Okay, now the first statement is quite obvious from the definition of an infimum itself. That's something very obvious. Observe that if I choose an element T which is equals to mu A of x plus epsilon, and S which is equals to mu A of y plus epsilon, that is, they both are not the infimums according to the definition of the Minkowski's functional, and this is for some epsilon greater than 0, then xt inverse this element and as well as yt inverse this element, both of them belong to A, right. And since A was a convex set by our hypothesis, therefore a convex linear combination of them, which we give like this: see, x plus y by s plus t is equals to, so how can I write it? I can write it as t times t by s plus t times x by t plus I have s by s plus t times I have here y by s, right. This is x by t, y by s, and from here it's obvious, right, using this and using this. So this implies that mu of x plus y, this should be less than equals to mu of x plus mu of y plus 2 epsilon, and this happens for an arbitrary epsilon greater than 0, right. And so we have the necessary inequality. Okay. So this is the proof of A, and B and C are sort of immediate, right. So B is from definition, it immediately applies from the notion of taking infimums and then scaling the elements upon which the infimum is taken. That's quite obvious from the definition of infimum, and C immediately follows from A and B. Fine. Okay. The D part is a sort of to observe. See, by the way it is structured, we have this, right? Mu c is less than equals to mu a is less than equals to mu b. This is something which we have by the mere definition of B and C. Now fix x in capital X and choose S and T such that let's say mu c of x is less than S is less than T. Fine. Once we do this, this implies that x by S or xs inverse, whatever you want to talk about, is in C, and which implies that mu a of x by S, this is less than or equals to 1, right? Or rather, this will be more accurate if I say that moreover, or rather I should use it like moreover mu a of x by S, this should be less than or equals to S by T, and this is less than 1, right? This implies that x by T is in B, which implies mu b of x is less than or equals to 1, and this holds for all T, and this holds for all T greater than mu c of x, which implies that mu b of x this is less than or equals to mu c of x, and a similar argument will prove that mu b of x is less than mu a of x is less than or equals to mu b of x. So just traversing around the inequality we are done, or rather this inequality itself does the job. Okay. I do not need to show the other inequality, this does the job itself, right? Fine. Now let us examine one more important property of the Minkowski's functional, and then we will be targeting our main result, which is the notion of when a topological space is normable. Okay, that is what we will be essentially requiring to study. Fine. Okay, so the theorem is as follows. Suppose B is a convex balanced neighborhood am I doing something wrong? Okay, so I have a convex balanced local base in a topological vector space X. Associate to every V in B a Minkowski's functional mu V. Okay, then A, that if V is equal to X in X such that mu V of X is less than 1 for all V in B, and number B is that if I choose this mu V such that B is in B, then this is a separating family. This is a separating family of continuous seminorms. Okay, yeah. So essentially, this is what we have, and let's check the proof of it. Okay, proof. Okay, wait a second, I need to verify something. Just a minute. Yeah, I was thinking about the hypothesis. No, I guess it's on convex balanced will do, right? Yeah, I guess it will do. Okay, fine. Okay, okay. Let's see the proof. Okay. Now if x is in V, then x by t is in V for some t less than 1 as V is open. Hence what do we have? Hence this proves that mu V of x is less than 1, right? Now if x is not in V, then okay, I am getting the point, right? Yeah, if x is not in V, then x by t is in V, which implies t must be greater than or equal to 1, and this is why as V is balanced. Fine, right? Okay. Okay, so B is a convex balanced local base, right? So V is a convex balanced neighborhood. Yeah, right. Okay, as V is balanced. Fine, fine. Okay, I think this should be capital V. This looks like an element rather, but this is capital V. We are talking about the set. Okay, as V is balanced, right? So this implies that mu V of x is greater than or equal to 1. Thus, what we conclude from here is that if I choose out an element from V, then the Minkowski's functional is less than 1, and if I choose an element outside of V, then its Minkowski's functional is greater than or equal to 1. That means that V must be exactly identical to this set itself, the collection of all those elements whose Minkowski's functional is less than 1. Fine, this proves part A. Okay, wait a minute guys, wait a minute. Okay, right? Yeah, now let's prove part B. Now part B is actually very easy to prove. See, mu V is already a seminorm, right? We have already seen it is already a seminorm because we are already given a convex balanced neighborhood, right? So once it's convex, basically it's absorbing, to be very specific, it's a neighborhood, it's an element of the local base, right? So it's absorbing it's trivially by the definition of local bases or by the topological property of the local bases, and the convexity and balancedness is given by hypothesis. So it is essentially a seminorm, that's quite obvious. So what we need to show is that it's continuous, but continuity is again very easy to observe because of the properties of the seminorm, right? Why is it so? See, if r is greater than 0, then the mu Vx minus mu Vy, this is less than or equals to mu Vx minus y, and this is less than r. Okay. Now if x minus y is in Rv, sorry, I'm extremely sorry, this happens if x minus y is in Rv. Fine, fine enough. Okay, yeah, so this immediately implies that, see, if x minus, yeah, right, this immediately implies that mu V is continuous by definition itself, right? So what all we need to prove more is that it's separating, right? Now if x is in X such that x is non-zero, so then if x is non-zero, then x is not in V for some V, for some V in the balanced in the collection of all local bases, convex balanced local bases. For this V, you can immediately observe, for this V, mu V of x is greater than or equal to 1, hence non-zero, right? Which means mu V is a separating family, is a separating family. Fine, fine. Okay. Now we come up with one more theorem which we are not going to prove but rather state. The theorem is as follows, that suppose P is a separating family of seminorms on a vector space X, then associate to each element small p in capital P and to each positive integer the set Vpn equals to x such that p of x is less than 1 over n. Fine, we can do this. Let B be the collection of all finite intersections of VPNs. Okay, we are going towards talking about a basis for a topology, nothing else. Like if you recall that if you have a topology, then we have something called a subbasis. We take the finite intersection of all those elements in the subbasis, and then that forms a basis, and then taking arbitrary unions will give you the topology, right? So this VPN will actually serve as a subbasis for the topology of the topological vector space, or rather we can induce a topology. Okay. So once we do this, then B is a convex balanced local base for a topology tau on x, which makes x into a locally convex space. Just as I said, right? In fact, it just not deals with the topology, but uses some additional conditions such that number 1, for all p in P is continuous, and number 2, E in X is bounded if and only if P inside P is bounded on, right? So the mere reason for giving out this theorem is that we have a separating family of seminorms using which or rather which we can treat as a subbasis for to induce a topology, and the topology is specifically a locally convex topology with the additional structures that each of these seminorms are continuous, and a set inside X is bounded if and only if each of these seminorms are bounded on that set. Okay. So that is what you need to take from this theorem. Fine. We are not proving this theorem, let it be. And the final theorem which we are going to talk about now is when is a topology normable. Okay, theorem, and this is the important one to take away from here, is that a topology or a topological vector space X is normable if and only if its origin has a convex bounded neighborhood, has a convex bounded neighborhood. Fine. Let us see the proof, and one part of the proof is quite trivial, that is if X is normable, then we can just work out with the norm, right? Then the norm on X is compatible with the topology on X, say tau, and this implies that this collection X in X such that its norm is less than 1 is the required neighborhood. You can clearly see that it's a convex neighborhood and it's a bounded neighborhood of the origin, right? So the converse part is what non-trivial in this case. So let us prove that. Conversely, suppose X has a convex bounded neighborhood at the origin, say V. Okay, so I am choosing a convex bounded neighborhood, say V. I need to come up with a norm, that's it, and the norm will be exactly using the Minkowski's functional, because that's what we have developed so far, right? Right. But then recall, then that means that V contains a convex balanced neighborhood of U, a convex balanced neighborhood of neighborhood U of the origin, right? And U is bounded as well, because V is bounded. U is bounded as well, right? Now what we do is that we simply choose the norm of an element to be mu of x, where x is in x. Fine, right? Okay. Or rather I should write mu u of x. Okay, that is mu is the Minkowski's functional of u. Fine. Now if I scale u by some positive number r, now Ru forms a local base, for tau. Tau was the topology on x. If x is non-zero, then x is in Ru for some r greater than 1, which implies that norm of x is greater than or equal to r. And if I consider this to be star, which implies that star defines a norm, right, from the definition of the Minkowski's function. Okay, right, this is one part. And by the definition of the Minkowski's functional, and since u is open, we can say that also by the definition of the Minkowski's functional, and that u is open. So from the previous theorem we can see that x such that norm of x is less than r, this is equals to Ru for all r greater than 0. Thus the norm topology coincides with tau, and that's the end of the proof. Okay, yeah, so this is by far now the end of this series. We'll try and come up come up with some more more content for this series itself, but for the time being we are currently stopping this series. There are more topics which are coming soon on this channel. We will get to see some problem solving sessions on algebra, and then we might also get a series on measure theory. It might come. If it comes, it will be taken by me itself. And there are some more updates which will be surely given to you via Jyotishko, who is the owner of this channel. And please stay tuned to to come up with some more interesting topics related to advanced mathematics. So get going, and signing off for now.